Welcome to the course on electromagnetic theory and interference. In this session, let us see how to find the transmission line equations. So in the last session, we have seen a two-conductor transmission line is able to support a TEM wave. In that, electric and magnetic fields are perpendicular to each other and transverse to the direction of wave propagation. Important property of TEM wave is that both electric and magnetic fields are uniquely defined by voltage and current from the Faraday's law and Ampere circuit law. So V is equal to minus integral over the line E dot dl, and current I is equal to closed integral over the line H dot dl. Based on this, we are going to use the circuit quantities, voltage and current in solving the transmission line problems instead of going for the field quantities E and H, where we are going to solve by using the Maxwell equation and boundary conditions. Why we choose circuit quantities means the circuit model is simpler and more convenient. We have already seen the two conductor transmission line equivalent circuit is represented by uh, resistance and inductance in series and conductance and capacitance in parallel. We are going to examine this small portion del Z of a two conductor transmission line, and we are going to find the line equations here. Here the wave propagates along the positive Z direction from the generator to the load. So the generated voltage and current are represented by V of Z comma T and I of Z comma T, and all the transmission line parameters RLGC are represented by means of its incremental portion of length del Z. And at this junction, del I current flows into this parallel combination, and to the load I of Z plus del Z comma T current flows. Similarly, the voltage. So we are going to use the two circuit laws. One is KVL and KCL. First, let us apply the Kirchhoff's voltage law to the outer loop of the circuit, where the applied voltage V of Z comma T is equal to the sum of the voltages across the entire outer loop, right? So V equal to I into R. Okay, R we are representing R into del Z, and similarly L del Z into dou I by dou T, and the voltage across the load. We are going to represent the voltage as difference between the load and the generator. So we are rearranging this term in such a manner that because it's going to be a negative term when it comes this side, right? So take minus outside, and here this is a positive term, so give a difference here. So we are going to take this difference as dou V of Z comma T and the numerator, and del Z is going to be 0 here. We are going to apply that limit. So dou V of Z comma T by dou Z is equal to R into I Z comma T. The del Z we have taken already, L into dou I of Z comma T by dou T. Similarly, by applying the KCL, Kirchhoff's current law, to the main node, I of Z comma T is equal to of sum of entering current is equal to sum of leaving current, del I plus I of Z plus del Z comma T. But this uh, I of del I current, okay, is flowing in this parallel combination. So how can I represent the current? By means of G into V, okay, the voltage across the load, and C into dou V by dou Z. But we have to consider the voltage at the load here. So similarly, we have to rearrange the current components on one side, okay, and other things on the other side. So we will get similar equation like the voltage dou I of Z comma T by dou Z is equal to GV of Z comma T plus C into dou V of Z comma T by dou T. So we assume the time harmonic dependence V of Z comma T is going to be the real part of Vs of Z into e power j omega t. Similarly, the current. This Vs of Z and Is of Z are the phasor form of the voltage and current terms, which is a function of both Z and the time. Okay, position and time. If we apply these to the already obtained equations here in of this dou V of Z comma T by dou Z, we are going to replace by dVs by dz. And here uh, the RSR will we will get into IS we will get plus L into instead of dou by dou T j omega we have to take. Okay, and L will be there. Is is there. So Is is common, we have taken out. So R plus j omega L into Is. Similarly, in this current expression, if we apply in terms of phasor form, dIs by dz is equal to G plus j omega C will come into V of S. So these differential equations are coupled equations. So voltage and current are coupled. To separate them, we need to take the second derivative of this particular equation. And while taking the second derivative, we get the first order derivative for current, and that we are going to apply this ninth equation to the eighth, right? So dou square Vs by dou Z square is equal to R plus j omega will be there, and dis by dz will be there. Instead of that, we are going to substitute this particular term, G plus j omega C Bs. And already negative sign is there, one more negative comes, so entire equation is positive. So d square Vs by d is square, this entire term I am taking the left hand side, minus gamma square Vs is equal to 0. So this gamma is going to be alpha plus j beta as we seen in the last unit, and that is going to be equal to what? The root of this gamma is going to be what? Root of R plus j omega L into G plus j omega C. By taking the second order derivative, okay, and applying the same thing, same logic here, by taking second order derivative, this first order derivative for Vs, if we apply, we get the similar equation for current. So d square Is by dz square minus gamma square Is is equal to 0, right? So we can observe that the wave equation for voltage and current, these are the wave equations for voltage and current in transmission line. These are similar to the form we obtained for the sine waves. So here gamma is the propagation constant, is measured in per meter, and alpha is attenuation constant, is measured in amperes per meter or decibels per meter, and beta is a phase constant, okay, which is measured in radians per meter. The wavelength, we know the relation, it is 2 pi by beta, and velocity we know it is omega by beta. I can write the frequency into lambda also. These are the other ways of representing. The solution to the above wave equations, okay, d square v is vs by dz square minus gamma square vs is equal to 0 is vs of z is equal to sum of forward traveling voltage and reverse traveling voltage. Okay, V naught plus e power minus gamma is it, is a voltage traveling along positive z direction, plus V naught minus e power gamma is it, is the amplitude of the voltage wave traveling in negative z direction. Similarly, current expression is given here. So V naught plus I naught plus V naught minus I naught minus are the wave amplitudes. Okay, these signs represents the voltage is traveling along the positive z, and this here it is traveling along negative z direction. The solution to our voltage and current equations in our transmission line. So the instantaneous expression for voltage, how will we obtain? We already saw that V of Z comma T is going to be the real part of Vs of Z into e power j omega t. So we have found solution for Vs of Z. V naught plus e power minus gamma Z. So we are going to substitute the Vs of Z from this expression of solution of the wave equation. So we get V naught plus, instead of e power minus gamma z, we are going to apply e power minus alpha is it, okay, gamma is alpha j beta. So e power minus alpha is it, e power minus beta is it will be there along e power j omega t. E power j term only we are taking the real part, so we get cos omega t minus beta is it for this particular term, and plus v naught minus e power, here it's positive, so alpha is it will be there, and all the terms are positive, cos of omega t plus beta z. Characteristic impedance of the line is going to be the ratio of positively traveling voltage wave to the current wave at any point on the line. We know that resistance is the ratio of voltage and current. Similarly, the characteristic impedance is the ratio of positive traveling voltage to the current wave at any point. This characteristic impedance is that not is analogous to the intrinsic impedance of the medium of wave propagation. So we are going to find the exact value of the characteristic impedance here. How we are going to do is we are going to substitute these two expressions, okay, in the already existing these expressions. First we have found, right, the voltage and current equation in terms of this transmission line parameters. We are going to apply here by taking the derivative, and we are going to equate the coefficient of e power gamma z and e power minus gamma z. So let us take first the voltage equation, and we know the solution for Vs. It is V naught plus e power minus gamma z plus V naught minus e power plus gamma z. So here we are going to take just a differentiation of that. So this is a constant. If we take the differentiation of e power minus gamma z, it is e power minus gamma z into minus gamma. Similarly, plus v naught minus e power gamma z into gamma. And the rest of the terms will be there. Instead of is, we apply this solution for current equation. And if you simplify this and equate the coefficient of e power minus gamma z at first, let us see gamma into v naught plus is equal to r plus j omega l into I naught plus. Okay, that is a term for e power minus gamma z, right, coefficient. Similarly, we can equate the coefficient of e power plus gamma z also. In that case, minus gamma into v naught minus will be there. Same r plus j omega l into I naught minus we will get. Can take the current equation also and do the same. In that case, we can write the characteristic impedance is the ratio of forward traveling voltage to the forward traveling current, and similarly it is a negative of the of reverse traveling voltage and reverse traveling current. So from this expression, we can find it is going to be r plus j omega l divided by gamma for v naught plus by I naught plus, or minus of v naught minus by I naught minus. Similarly, if we do for the current, we will get the second term. This is gamma by g plus j omega c. We already know the value of gamma, right? It is going to be root of r plus j omega l into g plus j omega c. So we are going to put that particular gamma here. So one term in the denominator, whatever we got, we can write twice the root of this, right? Similarly, generally we will write 4 as root of 4 into 4. In this case, one root will get cancelled and we get this term r plus j omega l divided by g plus j omega c. So the characteristic impedance is going to be the real part plus some imaginary part, reactance. Resistance plus reactance we will get. So we should not mistakenly take R naught for the resistance R that we measure in ohms. Okay, this is in ohms per meter, that is the transmission line parameter, but this R naught is in ohms only, which is coming in the characteristic impedance. Propagation constant gamma, characteristic impedance is it not? They are the important properties of the transmission line because these depend on the transmission line parameters R, L, G, and C, and also the frequency of operation. Okay, from this omega term, we know it is 2 pi f, right? And we can find one more thing called characteristic admittance, which is represented by Y naught, which is the reciprocal of characteristic impedance. The transmission line so far we have considered here is lossy type. Lossy means what? The transmission line so far we have taken into consideration as a lossy one, where the conductors are imperfect, that is conductivity is not equal to infinity, and dielectric in which the conductors are placed is a lossy, that is conductivity for the dielectric is not equal to 0. Okay, so taking this as a general case, this lossy transmission line as a general case, we are going to consider two more special cases called lossless transmission line and distortionless line in the upcoming session. Thank you, everyone.